This lecture is on the chi-square test for independence. This test is used to assess if a significant relationship exists between two discrete, that is, categorical variables. That means that the two variables are measured on a nominal or ordinal scale. For a chi-square analysis, the data are considered to be non-parametric. That is, because we're talking about categorical data, we don't have the opportunity to gather information like means, standard deviation, sum of squares, or variances. The data for a chi-square test is going to simply be based on counts, or what we refer to in statistics as frequencies. In other words, how many subjects fall into each category or each level of the two independent variables. What we take then are the observed frequencies or the observed counts and then compare them with the expected frequencies. That is, what we would expect to observe if the null hypothesis was true. As always, the null hypothesis is going to state that there is no relationship between the variables. Thus, the test is called the chi-square test for independence because we are testing whether or not the two categorical variables are independent of one another. The data are presented a little bit differently in a chi-square test. If you take a look at your handout, you will notice that the frequencies are actually presented in a table format. Because the chi-square test is a squared value, the answer or obtained value will always be positive, and the corresponding critical values will always be positive. Thus, if you perform the analysis and you come out with a negative value at any time, you have done something incorrect. So let's go ahead and take a look at an example of how the chi-square test for independence would work. We're going to read through the example, look at the table of data, and then go through the 5 steps. Lastly, we'll talk about how we measure effect size for the chi-square test. In the example, a scientist would like to know if there is a relationship between handedness and eye preference. That is, which hand do you tend to use and which eye do you tend to use? Let's take a moment and see how you would compare to the subjects in this analysis. Think about whether or not you are right-handed or left-handed. Usually people have a dominant hand. And then close one eye. The eye that you keep open is considered to be your dominant eye. Most people tend to be right-handed and they are right eye dominant. We would call that a right-right preference. But sometimes there is a discrepancy. For instance, a person may be right-handed but prefer to use his or her left eye, and that may be for a number of factors. It's possible that the vision is better in the opposite eye. So just wanted to take a moment to see how you compare to the subjects in this study. So the scientist selects a random sample of 150 participants. For each participant, the scientist determines 2 things: whether the person is right-handed or left-handed, and whether they use their right eye or left eye when looking into a camera viewfinder. So we're going to use the data in the table to determine whether or not a significant relationship exists between hand preference and eye preference. And we're going to assume that alpha, or the type 1 error rate, equals 0.05. So let's take a look at the table. In the table, we have 150 participants, and what the scientist did was note which hand they used and which eye they used to look into a camera viewfinder. From his subjects, 20 were left-handed and preferred to use their left eye. 40 were right-handed and preferred to use their left eye. 10 were left-handed and preferred to use their right eye, and 80 were right-handed and preferred to use their right eye. Now you'll notice that these are natural data. They haven't been manipulated in any way. So in a chi-square test, there is no experimental manipulation, at least for this analysis. And you will notice that in general, there are more right-handed people. If you add up the column of right-handed people, you get 120. If you add up the column of left-handed people, you get 30. That's because in the general population, only about 10% of people are left-handed, so that makes sense. We probably wouldn't see an equal number of left-handed people and right-handed people in the sample, and that's okay. The chi-square test will take those ratios into consideration. If you look at the handout, the first thing we're going to do in step 1 is set up the null and alternative hypothesis. The null hypothesis is written in words because, again, like I said before, this is a non-parametric test. There are no means, there are no numerical values to really consider besides the actual counts. So we are going to write the null hypothesis in words instead of using parameters like we would commonly do. So the null hypothesis for the chi-square test would state that there is no relationship between handedness and eye preference, or no relationship between hand preference and eye preference. The alternative hypothesis is also written in words, and this would just be the converse. The alternative would be that there is a relationship between handedness or hand preference and eye preference. For step 2, we are going to determine the critical values. For the chi-square test, the critical values no longer depend so much on the actual number of subjects observed, but on the table of data. So you're going to see slightly different symbols for degrees of freedom. In step 2, the degrees of freedom is equal to the number of rows minus 1, where rows is represented by the letter R, times C minus 1, or the number of columns minus 1. So in this particular table, we have 2 rows and 2 columns. So our degrees of freedom calculation would be 2 minus 1 times 2 minus 1, which equals 1. In order to determine the critical value, we're then going to look at the table of critical values for the chi-square test. For this particular test, we have 1 degree of freedom. So if you look at 1 degree of freedom for an alpha level of 0.05, the corresponding critical value is approximately 3.84. So when we perform our chi-square test in step 3, we are going to determine whether or not our obtained value exceeds this critical value. That will be our decision to make in step 4. The critical value distribution is similar to that for ANOVA. Again, they're all positive values, and we have a one-tailed critical value distribution. For step 3, we're going to perform the chi-square test. And the calculation for step 3 will actually be divided into 2 parts. The first part is to find what we would call expected frequencies for each cell in the table. And by cell, I mean each possible combination of the levels of the 2 independent variables. Our current table in this example has 4 cells: left, left, right, right, and right, right. So we are going to find the corresponding expected frequencies for each of those cells. What we have in the data are what we call the observed frequencies. That is what the scientist actually observed in the sample. The expected frequencies will not necessarily all be the same value because they take into account the distribution of the frequencies or counts in the table. So if you look back at the original table, notice the counts were not all equal. They weren't even close to being all equal. And the expected frequencies will take that into consideration. In order to calculate the expected frequencies, what we're going to do first is add up all of the columns and add up each of the rows. These column totals and row totals will be used to calculate our expected frequencies. So on your handout, we've gone ahead and done that. You'll notice that for hand preference, we have 30 left-handed and 120 right-handed. In terms of eye preference, we have 60 left-handed and 90 right-handed. Both the row totals and the column totals should add back up to n, and in this case they do. If you're adding up the columns or adding up the rows, they all add up to 150 total subjects. In order to find the expected frequencies, and you'll notice that is represented by a small letter F with a subscript E, we are going to multiply each cell's column frequency by its row frequency and then divide by n. So taking the first cell, the left cell, that has an observed frequency of 20. To find the corresponding expected frequency, we will multiply its column total, which is 30, by its row total, which is 60, and then divide by 150, which is n. When you perform that calculation, you will come out with a value of 12. We're going to continue this pattern for the remaining 3 cells. So we're going to move down next to left-handed people with a right eye preference. For that cell, the observed frequency is 10. To find the expected frequency, we're going to multiply its column frequency, which is 30, by its row frequency, which is 90, and divide by 150. Oh, sorry. That will come out to be 18. Let's back up for a second and we'll go to the right-left cell that has an observed frequency of 40. Again, we're going to multiply column frequency times row frequency and divide by n. In this case, the column total is 120, the row total is 60, and again divide by n, which is 150, and that will give you a value of 48. Lastly, we will do the right cell that has the observed frequency of 80. Column frequency times row frequency is going to be 120 times 90, and then dividing by n, or 150, will give you a final value of 72. So for this first part of step 3, we're finding an expected frequency that corresponds to each observed frequency in the cells. Notice they are all different values, and that is quite common. It is important to make sure that you keep each expected frequency with its corresponding observed frequency, because that information is going to be used to actually compute the obtained value for the chi-square test. So the second part of step 3 is to calculate chi-squared obtained. If you look on your handout, the formula is the sum, and then in the numerator we have observed frequency minus expected frequency squared divided by expected frequency. So you are going to have that piece for each cell, because this particular analysis has 4 cells. We are going to have 4 pieces. We're going to do the first cell first. So the observed frequency in that cell is 20. Now we know that the expected frequency is 12. So in the numerator we would put 20 minus 12 and then square it. And then in the denominator we would divide that by 12. For the second cell, right hand, left eye, the observed frequency is 40. The expected frequency that we determined is 48. So in the numerator we would have 40 minus 48 squared, and then divide that by the expected frequency for that cell, which is 48. For the third cell, the left hand, right eye, we have an observed frequency of 10, and we now know that the expected frequency for that cell under the null hypothesis would be 18. So we would take 10 minus 18 squared and then divide that by the expected frequency of 18. Finally, for the last cell, that's right hand, right eye, the observed frequency is 80. We will subtract 72, which is the expected frequency, and then square that answer, and then divide by 72, the expected frequency. So if you do each of those parts, you should come out with about 5.3, and then 1.3, and then about 3.6, and then about 0.9. And if you take it out to 2 decimal places, you will come out with a final chi-squared obtained value of 11.11, although 1 decimal place is just fine. So notice again, the pattern to find chi-square obtained is to have as many of those little pieces as you have cells. If you had a table that had 6 cells, you would have 6 of those pieces. If you had a table with 9 cells, you would have 9 of those pieces. One of the most important things to remember, and a common mistake that is made, is that you must divide each of those little pieces by the expected frequency. It is very easy to accidentally put in the observed frequency in the denominator. So make sure you're doing the expected frequency in the denominator for the test. So we can move on now to step 4, making a decision regarding the null hypothesis. For this analysis, our obtained chi-square value is 11.1. The critical value was 3.84. And using the logic that we always use for making a decision, our obtained value exceeds the critical value in this case. That is, 11.1 falls past the critical value cutoff of 3.84. Therefore, it falls into the rejection region, and we would reject the null hypothesis. In order to interpret these results in an APA formatted sentence, when we have a significant result, we would first say that there is a significant relationship between our variables, but then we have to make an additional statement as to the nature of the relationship. For a chi-square test, simply saying that there is a relationship is not enough because it doesn't give the reader the idea of how they are related or what the trend is within the data. We don't know, okay, do left-handed people prefer to use their right eye? Do right-handed people prefer to use their right eye? In other words, simply making a statement of that there is a significant relationship is not enough information in a chi-square test. It might work for other analyses, but not for this one. So you'll notice the sentence for step 5 is a little bit longer than usual because there are actually 2 statements. First, there is a relationship between handedness and eye preference, or you could also say there is a relationship between hand preference and eye preference. Then we put in chi-square, and in the parentheses, the chi-square report is a little bit different. The first number is the degrees of freedom, as always. In this case, it's 1. But we are also required to include the sample size. So you see chi-square with 1 degree of freedom, comma, n equals 150. So both pieces of information have to go into the parentheses, both the value for degrees of freedom and the value for n. So end parentheses, and then you put your actual obtained value, which in this case was 11.11, and then because it was a significant relationship, p is less than 0.05. The second part explains to the reader the nature of the relationship, and there is more than one correct way to say it. That is up to the person performing the statistics to report how the 2 variables are related. I simply wrote, right-handed people prefer their right eye, and left-handed people prefer their left eye. If in step 4 we had a chi-square obtained value that was less than the critical value, and our decision was to accept the null hypothesis, you would not need that second sentence because there would be no significant relationship to report on. In other words, if you end up accepting the null hypothesis for this test, you would simply write out the first sentence, and of course you would have no significant relationship, and p would be greater than 0.05, and that would be the end of your APA formatted sentence. You would not need to include a sentence that explains the relationship because there is no significant relationship to explain. The last part of the handout takes you through the measures of effect size for the chi-square test. There are actually 2 available measures for the chi-square test depending on how large the table is. The first one that you see is called the phi coefficient. The phi coefficient is used if you have what we would call a 2 by 2 table, which we have in the example that we just went through. That is, each variable has only 2 levels. A 2 by 2 table. So the phi coefficient would be suitable in those cases where you have a 2 by 2 table, or you are trying to relate 2 independent variables that each have 2 levels. To find the value for phi, you use the chi-squared obtained value, divide it by n, and then take the square root. So it would be chi-square obtained divided by n, and then take the square root. So in our current analysis, that would be 11.11 divided by 150, then take the square root. When you perform that calculation, you will come out with a value of about 0.27. And to evaluate the phi coefficient, we use the values that are specified for r squared. So this would represent a large effect. Now it's interesting that we use the word effect size or the term effect size when really this analysis is about relationships, because there is no manipulation of one variable on the other. So we say effect size, but there really isn't an effect to measure. It's more a measure of relationship strength. So we could say there's a large relationship, but we just tend to usually say large effect when we say the phi coefficient. If you have a table that is larger than 2 by 2, that is if one of your variables has 3 or more levels, or both of your variables has 3 or more levels, we use a slightly different measure of effect size known as Cramer's V. Cramer's V is very similar to the phi coefficient, but it has one additional piece in the denominator called degrees of freedom star. Degrees of freedom star is the smaller of either the number of rows minus 1 or the number of columns minus 1. So if you had a 3 by 2 table, if you had 3 rows and 2 columns, if you had 3 rows, the value of r minus 1 would be 2. If you had 2 columns, the value for c minus 1 would be 1. So you would use the smaller of those two values, which in that case would be 1. Otherwise, the formula is identical to that of the phi coefficient. Chi-square obtained divided by n times this new value, degrees of freedom star. To interpret Cramer's V, it depends on what your values for degrees of freedom star is. If degrees of freedom star is 1, you'll notice on your handout that a small effect are values between 0.1 and 0.3. A medium effect are values between 0.3 and 0.5. And a large effect are values greater than 0.5. As your degrees of freedom star becomes larger, on your handout you see degrees of freedom star is 2 and degrees of freedom star 3. You'll notice that what is considered a large effect becomes smaller. In other words, you can have a smaller calculation for V and still have it considered to be a large effect. If you have degrees of freedom star of 2, all you need is a value of V of 0.35 to be considered a large effect. And if degrees of freedom star is 3, you only need a value of 0.29 for V to come out with a large effect. So as always, the measure of effect size would just be added on to the sentence in which we report our chi-square test results. So depending on the size of the table, you will have to determine which measure would be more appropriate. Phi coefficient if you have a 2 by 2 table, and Cramer's V if you have a table that is larger than 2 by 2.